Hello, I'm going to introduce my project on cerebellum isolation using 3D UNet. So the aim of the project is to isolating the cerebellum from the whole head. So here, this is one of the example from the subject we have. So on the left, we have a whole head, which is a typical MRI images that we see, and let's say for whatever reason we need to isolating the cerebellum from this image. Normally we need a mask that are filled with the 0 and 1s, which one indicates the cerebellum, and we can multiply the image with the mask to give us the cerebellum. So now um, the goal of my project is to generate this mask. Our approach is to using 3D UNet to generate such a mask. So this is an overall architecture of the UNet. Here we have a T1 image or T2 image that concatenate together to fit it into the UNet, and UNet will have multiple encoders and decoders to be trained to learn the features from the images and produces the mask. So here the input channel for the encoder one, which is the initial encoder, will be 2 channels for T1 and T2. Then they start producing the number of the channels out here, which called initial feature number, which is defined as initial feature number. By default, it's 16, but this number can be adjusted by and this is the detailed structure for the encoders and decoders, also the bottleneck. So for each block, it has 6 layers. The first one is the convolution layer, which just perform the 3D convolution over the image. And after that, we have batch normal and leak value, and repeat these 3 layers again to get our encoder or decoder blocks. So this block will take a number of channels input and producing the output with a certain number of channels predefined. So for example, for here, the encoder one will take 2 channels in and do the convolution operation twice and producing 16 channels, then 32, and keep going down until reach the bottom. The red arrows are the downsampling, which just reduce the image size into half, and the yellow arrows will be upsampling, which just reconstruct the image size to twice. And the blue lines here are the skip connections that exist in the UNet. And after that, we have a final convolution layer to reduce our to generate our mask and get a softmax to have our final probability mask. Before we put the data into UNet, we need to do some pre-processing for the data, because the images are in the original space, and we need to translate them into a template which the cerebellum will be consistent in the locations, and the model will not be influenced by those inconsistent spatial information. So let's take a look at one example. So in the original space, the head can be in a different location, have different orientations, but after the affine and we have the head in the template space, this is a kind of stable here. And we predefine a cerebellar bounding box, which contains all parts of cerebellum and a larger. And this cube will be used for the model. And other information about the head is not really the task, so we don't really need to put all of those the whole image in the model. So on the right, this is the final data that the model actually gets. The blue is our the blue volumes will be where the masks labeled as 1. Right? So once we have our training data, we can start training our model. So first, I test with the different training process and with the different initial numbers. So on the training, they all perform similarly. And on the testing sets, we do see that more initial number of channels will give us better results, but also it requires more training time. So on compromises, we use the 16 as default, but they can be increased if later on we need our model to be more accurate. And this is the training process tested with the different loss functions. So if we take a look, and you can see the after a certain number of training, we can see the test error actually start going up a little bit. So model might start overfitting. Okay. So this is one of the results that I got from the UNet. On the left, we can see the image that are in red as the probability maps from the UNet. And after thresholding and binarizing them, the mask, we have our final results. And compared with the ground truth we have on the right, we can see there's the model performs well on the most of the volumes, but there are some volumes on the surface that model actually are having trouble and made mistakes. Okay. To evaluate our model, we need some evaluation criteria. So the first one is a dice score. So it was calculated using this equation. To visualize how this actually means, you can take a look at this slice of the example. So if we have a grand truth on the left here, and our prediction from the UNet is the second image. So the first we calculate the intersection of them, which is just the volumes that exist on both grand truth and prediction. And then we calculate the union of the two images and divide the intersection by the union, and we have dice score. So intuition here is if we have the most, if we have more volumes are labeled correctly, the intersection will be very large, and the union, those volumes that are in the union, which are the gray, will be very less, and the dice score will become higher. So the higher the dice score is, the more accurate the model is. But there is a problem with dice score is that because in the cerebellum, most of the volumes are in the center and they will be labeled correctly, and the actual important volumes that model might make mistakes on the surface, and they are not really that much. So we need another criteria that are more sensitive to the surface and those critical location. And for that reason, we used another evaluation criteria, which is a Hausdorff distance. So it calculates in the formulas like from the right, and first we need if we have a set A and set B. First we for every for one point of set A, we calculate the all of the distance from this point to all of the points from set B, and and take the minimum of those distance which are labeled here. So this will be the first step, and we do it for every point of set A and get the maximum of those distance. So this is smaller h from A to B, but this is one way Hausdorff distance, and then there is a slight problem because this is not sensitive to the shape of the set B. So if we have an extra piece of circle here on the end of set B, the one-way Hausdorff distance will give us the same distance, but this is not what we want. So we need to calculate the two-way of a Hausdorff distance. So doing the same calculation, but from B to A, and get another distance and take the maximum out of this. So this distance will be sensitive to the edge, but also it will be sensitive to the outliers. So in order to increase the robust, normally we take 95 percentile of this Hausdorff distance. So those are some results from the model that we tested. So we can see the unit X actually perform much better than the average, which will be our baseline. And I also compared with suit, and you can see this unit X performs better than suit. Now let me start with some coding of details of coding. So I'm using PyTorch. Well, I would say if you want to use TensorFlow, it works very similar. So on the PyTorch, the first thing for the unit, well, we have to write the block first. So if you So if you check the diagram on this one, the blocks will have exactly the same architecture. So the first, well, the PyTorch gave us a lot of useful libraries function that we don't really need to code from the scratch. So the first one, the convolution, 3D convolution, and the batch normal, and leaky ReLU, and do it again. For all of the module that we implemented, we should always inherit the in.dot module. So this will give us other. This will make your block that are accessible by other code and or by the other piece modular or function. So like writing a block is as simple as that you have define a layer, or you can well, not necessarily, but I found it's easier that you define a layer here and then forward. Forward means that you put your data here, X, well, you can name it whatever you want, and then calculate the X based on how you defined your layer. Sequential means the data will flow those layers sequentially. Okay. Reasonable. And the next one is a downsample. So we have here from the encoder, we have downsample. So the purpose of downsample is to reduce the size of the image to half on each dimension, but increase the number of the channels, which we consider as features. So we define we have also the two channels. Also I forgot the convolution 3D. The first one is the in channel. The second one is out channel. So if you put one channel in, two channel out, then those numbers will be 1 or 2. So in the downsample here, we have one channel in, channel out. Sorry, no one. The certain channel that we have as we initialed. So this number will be given when you use this block. You have to give this certain number, and the convolution will give have this number of channel in, this number of channel out. But when we do the downsample, we need to well, the first we need to reduce the size of image, which is implemented by the stripe. So the stride means normally if you do the convolution, you do it 1 pixel by 1 pixel or 1 voxel by 1 voxel. The stride means that you actually skip one, so you move 2 at this 1 stride. Then do the batch normal, do the leaky. I'm sorry?
Why would you want to do the stride rather than going to the next one?
What do you mean by the next?
Why do we want to skip one? Yeah, why do you skip?
Just reduce the image to the half. So if I don't have, so if you have a skipping one voxel won't really losing any information potentially, because you remember you have a 3 by 3 by 3 kernel, and if you're looking at the first voxel, it actually contains the information from the surrounding voxel. So move too much, then you actually skip some part of the image. So that's the mistake, or that's the potential mistake that we will try to avoid. So if you want to do the stride equal to 4, then you have to increase your kernel size to make sure that you include those information that you skipped. And forward, the same thing. And upsampling here is a little bit complicated than downsampling, because for the UNet upsampling, we have a information that from the deeper layer, but also we have a skip connection that we have to concatenate from the corresponding layer. So that's why we have the first one is the transpose convolution, which is the inverse of convolution. So this stride equal to 2 will increase the number of the sizes. And we have a self layer, so this will be calculated. So now we have X and feature map. Feature map will be the skip connection that we take from the previous, the horizontal layer. So first up, X will be the data flowed up to the layer to the upsample block, and we put it in the self up to reduce the channel number, and we don't reduce channel number here, but to increase the size of the image. So so now it's the same size of the feature map, and we can concatenate these two group of features and then put it into the self layer, which will reduce the channel size from half to from the times 2 to the original. CDB, we're not using that anymore. Yeah, so now we have those blocks, so we can build our UNet. This is the initial feature that I was talking about. Now, yeah, as we have an encoder 1, 2, 3, and also the decoders, we put them in sequentially or any orders you like. And all of them are the same block convolution from 2 channel in and the 16 channel out, and downsampling, we have 16 channels into the downsample model block, and well, the downsample will give us 32 channel out. And those are different layers. The data will flow like this. So concatenate in T1 and T2. So now we have 2 channels, put in the encoder 1 here, and give us 16 channel out. So that's the result 1. Put in the downsample, and then put in encoder 2. The result 1, result 2, those are the data that flows down to this UNet, but also it's the feature maps that flows horizontally to the decoders. So that's why the decoders, the upsampling will have the information from the results from previous one, but also another results from the more previous ones, which are the feature maps. So that's the unit. Once we have that, we can, well, this is not necessarily, but normally we also implemented our data sets using one of these interfaces or something. Yeah, I think it's an interface. So in this way, we can use some functions to shuffle the data sets using this one line of code and not doing that with ourselves. So for these data sets, we need to define, well, this, if you use this interface, there are some certain functions you have to implement. And the get item, so the get item will return this certain data you want to have on these subjects.
Is this like a data frame?
Mhm.
Is this like a data frame?
No. Data frame is a table, right?
But okay, what is the functionality of this?
For this,
Yes, you said interface.
I think it's a way of that our organize the data, but the data frame is kind of install the metadata or information, right? So how do
What
I?
is a data structure? So
Yes.
what exactly are you doing here? So are you reading the images and
Yeah.
put them in the
Yeah.
in the structure, and then you can call them in different ways or split it?
Yeah.
So yeah, it's a data structure.
Yes.
Mhm. Okay.
So yeah, as we can see that when we implement, well, not implement. So when we call this class, we'll have a data set loaded on T1, T2, and the get item will how do I say this? So if you have a data set, I don't know if I have a, yeah, so here. So if you have something like this one, the SAC data set will return a data structure, which is data set that contains the data you wanted in this one, and you can call them, you can loop this data set with some functions like a data loader on the PyTorch. And for here, you can implement other functions like those ones are not mandatory, and you can implement them to if it's needed. But the mandatory one is the length and get item. The get item will be used on when you loop the data. So this when we have a data set, you want to get, let's say, the subject that indexed with 0. So this will be 0, the index, and the data set will return whatever you define here. So in this case here, I return a T1, T2, and the weight factor, which is not used anymore, and seg data, which is our mask. So if you want only T1, then you can modify this code and remove otherwise the other data. And when you loop the data set, the certain index will only give you the T1. So here you can see why I use this one. So define. Okay, let's see. Okay, so here I define a trainer, which interprets the different way of training. So the first one is the model, which model we want to train, and where we want to store the information, and data sets. Well, data sets to like which one so we want to train. Data sets we want to train, and combination is well, the combination is well, this is very personal, but it's for me, I split the data sets for 4 partitions and using 3 of them as training, 1 for testing. The combination means is if it's like the first one, the 1, 2, 3, then the extra 4, that means the 1, 2, 3 is training and 4 is for testing. Sometimes we might only want to test it a little bit, so we don't do all of them. But for a full loop of training, this is all of them. Once we have the trainer done, we once we have the trainer finished, the function will create the different folders of parameters, loss record, which record the loss, training loss, testing loss as we train, and running time. Just if later we need to see how long it took to run. There are the other ways that we can define from the training. So, for example, modality combinations. As we just saw, the 0 means T1, 1 means T2, and etc. Loss function, by default, it uses only cross entropy because that's what I found it has the best performance. But if you want to train with other functions, just give extra ones and feature numbers, default at 16. Yeah. So once we have all of them done, I'll create the folders, then store those information, and it'll start call the training. I think, yeah, call the training, which do the training job. So you see with this data loader. That's why we implemented the data sets. So the data loader can automatically load the data sets from those data set structure. And once you have that one, you can loop them. And for this data loader, it also gives you the different the parameters that define your batch size, whether you want to shuffle it or I think number of workers is how do you go with data. Yeah. So now it comes to the most part. So now once we have model which are passed as a UNet, we put it into a device. So that's required by the PyTorch. Normally, if you have a GPU, so that's where I define the device. If you have a GPU, your CUDA is available, you put it on the GPU, which makes the training much faster than on the CPU. But if you don't, the CUDA is not available, you have to train on the CPU, which just takes forever. You create a model, put it in the device, and then this is a idea of the model and whether this model is trained or not. So when we train the model, we actually find the best sets of the parameters that we need to use. So if you want to load a model from your previous train, you have to save those parameters you train, and now you load this parameter. So if the param path there is a parameters, then the model will load these parameters and put it in the model, which makes this model already trained. But if this is a nothing, the model will initial a set of parameters and start training. Well, then for our training, we need an optimizer, which do the back propagation to adjust the model. I use the Atom, which is a really common one and kind of a typical like one we use. It's more popular than stochastic gradient descent. And put the parameters. That the parameters is what we want to train in our optimizer. Loss is what recorded loss. So and we need to define a number of or we need to define a terminate condition for our training. So normally I used the how many times we want to train to stop it, but if you have a good feeling that how low you want your loss function to be, you can also use that one. Once you hit the lower value, it stops. It also works, but not typically useful. So for here, I train it 200 times. I think, yeah. Yeah, I forgot where I put this number. Yeah, here. So yeah, I trained it 200 times for the model. Yeah, once they start training, call another function which just train the model once and call this function 200 times. This will give us a little bit more ability to adjust whatever you want to train the model, because sometimes you want to only put T1 or something. So yeah, here, that's what another thing we need to do. So once we load those data also need to be put in the device, which is GPU in this case. Otherwise, you'll have errors that notify that those are not in the same location. And another thing that this is important. Sometimes it will give you error, sometimes it won't, and it will just give you the results you don't want. So it's a dimension. So for our 3D images, the model actually takes a 5D array, which the first dimension stands for batch, and the second one is channel, and the last 3 dimension is our images. So, but the T1, T2 we have is from the data, we actually have 3D images, and the data loader we just saw here will give us extra dimension for the batch, which makes those T1, T2 return here a 4D array. So that's why we need to unsqueeze this one an extra dimension here. So if you don't do that, it might work, but it won't give you what you want. Once you have the correct size images, and you can put in the model, and the model will give you a mask. Put a mask in the loss function you previously defined. Get a training loss. And this is also another thing that very important. To every time you want to optimize your model, first thing is to make all those gradients to 0. Otherwise, your gradients will build up, and I don't know what will happen, but that's a typical error that a lot of people make. Once the gradients become zeros, you can do the back propagation for the training loss, and the optimum step means that you have you adjust the parameters a step forward, or not forward, towards the gradient's direction. And this is just one fold or one training, and do it for 200 times. So after the training done, we need to save the parameters. So if you don't save them after the training, the program stops, so you lose all the results. So I save them after every 50 times of training, and save it to somewhere else called the PKL file. I don't think the suffix matters, but you need to save somewhere. Once we have those trained parameters, we can test our model. For the testing, it's basically similar to what to the training. We still do we still have the model. We need to give it a parameter path that the model will load. Give a test set, like which data set you want to test, and put it here. So yeah, so that's what I was talking about. So if you do with the index, this index will give you T1, T2 weight factor, and sec data, which is mask. The mask won't be used as testing. Then I write an extra file called, or function called predict. So the predict will first load the model. So if you have model here, put it in device, load load the parameter set, and return this model. So this model is already your previously trained. And if T1 is none, or just check if T1, T2 are appears. Also, on squeeze it twice, because this time we don't have the data loader to shuffle it and increase one dimension for batch dimension. So we have to unsqueeze it twice to make it a 5D array. So yeah, that caused me a lot of problems, and I took a lot of time to figure it out. Yeah, put it on device and put it on the model. So this will return a mask. This mask is also a 5D, sorry, the 5D array. So we have to unsqueeze them. Oh, sorry, we have to squeeze them later on when you save the images. So yeah, predict you have a mask template. Yeah, so here, well, I didn't squeeze. I just, well, I know that there's only one channel, one batch, so just using one, and save this image. This will so we'll have our predicted. This is probability masks from the model. So after that, we can have a evaluation. Yeah, this is the first one. Take the Y true Y prediction, calculated. Yeah, Hausdorff. I'll see if we have the. Sorry, I see you have the visualization for Hausdorff. Yeah, for the others, well, it's just different ways organizing the evaluation, but I don't think it go over the coder. Where is it? Yeah. Let's take off the. Okay. So evaluation, I evaluate different models. Well, not same model, but with different parameters. So when I save the parameters, I name them in some meaningful way. So for here, so this is the data set, subject, partition, which loss function I used to train which partitions was trained, training mode, which combination of model trained, and which data that we put in the model to test the group. If it's a train, which means that this score will be the training accuracy. Well, because this is the first partition, and this partition including this training partition, which makes a training group. So let's take a look at the test one. Yeah, for example, this one will be test because this subject in partition 4, but the parameters was trained on 1, 2, 3. So this is test. So this is the test results. This is really not arbitrary, but personal, like how you want to organize those results and visualize them. Okay, let's check the visualization. Yeah, most things I've already showed in the slides. This, yeah, here is one of the images that I was asked to see from T1, T2 in the same time, but more importantly, we want to plot those data and see if they actually separate separate in the space. So we can see that some of the tissues exist on somewhere in clusters, but not that separated. Where is the Hausdorff? Yeah, here. So I think the formulas for the Hausdorff is a little bit confusing, so I found it's better to show it on the graph. So so this, I load 2 images from the from data sets. One is the prediction, one is the our grand truth. So this is one slice from the grand truth. So now we calculated using the distance transform EDT to calculate the distance for each pixel from this cerebellum. So which means that, for example, if it's this pixel, it might this distance from this pixel to this cluster is the closer cluster is maybe here. So that's so we can see the more the pixel away from this cluster, the larger the value is, and inside this cluster it is 0. So this map is you can think of this map as a distance map that for each pixel that from the cerebellum, and we time it with our prediction, because what we are trying to calculate is the prediction, like from the ground truth. So all those areas are not important. So if we have a prediction that lay down here, so we time the prediction from here. So that's why we only extract those distance from this this thin layer, because inside all zero, it's always zeros. And we get the maximum of those numbers, which just give us the Hausdorff distance. So this, yeah, dice score. Yeah, I think the rest are similar to Everson and are all in my slides.
Out of curiosity, how long does it take to run your model? Like every time that you run it completely?
If I want to run it with all loss function, all partitions, all modality combinations, it takes around 20 hours or something. So that's why I normally only run with one partition, 1, 2, 3, and 4, and see how it goes. Yeah, but if you want to do for all of them, to have a full test accuracy, you want to do all folds. Yeah. The best way of finding all the optimum parameters are like initial numbers, loss functions, all of them is to run a full like grid search, but I normally do it one by one. So find the optimum number of the initial number, then set it to 16, then test another one.
But did you try it on the image with no cerebellum?
Mhm.
Did you try it using the picture, like the image with no cerebellum?
I mean, put an empty image or noisy image,
I
or
feel like some of the image that have no cerebellum part. Did you try it?
No, all the images that he is using,
Yeah, I feel like
they have cerebellum.
if you try it,
Oh,
I'm not sure what do you mean, try test it or just train
or
it?
just test it.
Not yet, but I would expect this to give us the what I thought of the spatial prior.
you mean a crop cerebellum?
Oh,
Mm.
cropped?
Yeah, imagine that you have an image
Mhm.
that doesn't have the full cerebellum.
Oh, yes.
And then you test the network with this one. Do you believe that your mask will be accurate?
No, that's what I tested here. Like once I shift 20 millimeters, some part of the cerebellum are already out of the boundary. So, yeah, that's why you can see it goes down flatly, then drop down immediately after here. So that's why, because part of the cerebellum has already been shifted out.
Right? Any question? Online, any question? Yes, no?
No, I think it was a great presentation.
No, I'm good.
Thank you.
All right. Well, thank you, Joe. Yes, a lot of work.
Oh, I apologize. It's a little bit messy, and I spent a lot of time organizing them, but that's another tip for you to start coding. I mean, it's better to have an overall structure in advance other than just fixing it. You see a lot of functions, I start calling them back and forth, and because I don't have that kind of a design at first, so I hard coded a lot of things. Then And later on, I figure out this part needs to be modified or repeatedly. So that's why I took this part out and write a new function. But that's not optimal.
Yeah, that's always, I mean, it's always hard because when you start a project, you don't have an idea of how far you will go in that.
Yeah.
But I mean, as a good practice, yes, like your functions needs to be, I mean, you shouldn't hard code and like hard code anything, right?
Yeah.
Everything needs to be flexible, and then you have an area where you can set all your parameters, and then you can modify functions and reuse code. This is kind of like the most important part, right?
Mhm.